So let me recall the statement of von Kampen's theorem. Of course, we already proved half of the statement last time. So X is a topological space, and suppose we have a covering of X consisting of two open sets U and V, such that U, V, and the intersection of U and V are path connected, and let X0 be a base point, a fixed base point, which lies in the intersection of U and V. I'm going to denote by JU the map at the level of fundamental groups induced by the inclusion from U to X. Similarly, I'm going to define or denote JV, so this should be pi1 of X, JV to be the map on fundamental groups induced by the inclusion from V to X, right? Of course, all the fundamental groups are taken with respect to the base point X0 here. IU is the map induced by the inclusion from the intersection of U with V into U. And similarly, IV is the map induced by the inclusion from the intersection of U and V into V. Okay, and with this setup, the theorem says the following. The map from the free product of the fundamental group of U with the fundamental group of V into the fundamental group of X is surjective. Right? What does this mean? That every homotopy class of loops in X can be described as a formal product of loops in U or in V, right? So remember, this map phi, capital Phi, is induced by the maps JU and JV, right? If I have a word on this free product, then I apply either JU or JV, depending where the symbol lives, and then I multiply them all together in pi1 of X. That's how this map phi is defined. It's a map which is uniquely determined by maps from pi u to pi1 of X and pi1 of V to pi1 of X. So we show that this map is surjective, right? And the second part of the theorem describes the kernel of this map. More precisely, the kernel of phi is the normal subgroup of the free product generated by the set of words of the form IUG inverse times IVG, where G is an element in the fundamental group of the intersection. IU, again, is the map induced by the inclusion from the intersection into U, and IV is the map induced by the intersection, by the inclusion of the intersection into V. So I think I'm using the following today. So it's equivalent, but I'll be considering the following. Yeah. It's equivalent, of course. Just take the inverse G, but I want to present it in this way. Psychologically, it's better. Okay.
Like we saw last time, this is going to be 1, right?
Sorry?
This was going to be the identity after you push through big phi. This element.
Yeah, you're saying this element is in the kernel in particular. Yeah, all of these elements are in the kernel of phi. Is that what you're saying?
Yeah, because like when we pushed through
Yeah.
phi, like we saw that it was 1
Yeah.
last time.
But I'm saying more, right? I'm saying that all of the kernel is generated by these guys. Not only that these are in the kernel, but the kernel is exactly the subset generated by these. So to expand on what Sophia said, let me convince you. Of course, in order for this to make sense, we should check that these are in the kernel of phi. So what is phi of IU, G, IV, G inverse? Phi, by definition, applies JU or JV to each letter of the word or to each symbol in the word, right? So in this case, we have JV, IU, G, JV, JU, IU, and here we have JV, IV, G inverse, right? But I claim that JU, IU equals JV, IV. It's the same map. Is the map induced? So this is a map from pi u to pi 1 of x, right? And I claim that each of these is exactly the map induced by the inclusion of u intersection v into x, right? And that follows because, of course, if the following diagram commutes, essentially. So IU, I can include u intersection v into u and then include it into x, or I can include u intersection v into v and then include it into x. And this diagram commutes, right? Doesn't matter if I go through u or through v, since it lives in the intersection. These are the same map, essentially the inclusion of u intersection v into x. So since this diagram commutes, both compositions induce the same map on
What's
fundamental
the
groups.
middle thing that you have? Oh, is that just meaning it commutes?
Yeah, sorry. This
Got
just
it.
means it commutes.
Yeah, okay.
Let's erase it. Yeah. So these two maps are the same map, right? That's what it means for a diagram to commute, which means that they induce the same map at the level of fundamental groups, right? And the induced map on fundamental groups are these: IUJU and IVJV. So these are the same map. So maybe I can just write here, introduce some notation and say this is the same as, I don't know, maybe JU intersection V, right? Or G. JU intersection V, or G inverse, where JU intersection V is the map induced by the inclusion, like that, by the inclusion of the intersection into X. So this is just the identity at X, right? So all of these elements are in the kernel, of course. But now I claim more. I claim that the kernel is generated by these elements. It's exactly a normal subgroup generated by this set of all of these guys. So an equivalent way of saying this is that the map phi, maybe let's call it phi tilde, the map phi induces a map phi tilde, which is an isomorphism from the free product modulo this kernel into X. This is an isomorphism, right? Because phi is surjective, so by the first isomorphism theorem in basic abstract algebra, you can kill the kernel and get an isomorphic group. Okay. Okay, so we proved the first statement, which was that phi is surjective, right? Now let's describe the kernel. So this was the proof of the first statement. So now we proved the second statement. So let me write N for the normal subgroup of the free products of U, pi1 of U and pi1 of G generated by this set. I'm mute. Okay, it's the same. Doesn't matter. Generated by this set, right? I'm gonna stick to this. I think I find it psychologically easier. Okay, generated by this set, where IU and IV are as we defined earlier. So let me introduce some terminology that I will use in the proof. Okay, so a factorization of a homotopy class in the fundamental group of X is a formal product of loops of the following form: F1, F2, up to F of K. It's like a string of symbols, such that Fi is a loop in U or in V based at X0. And bracket Fi denotes the homotopy class in the corresponding group, which is either pi1 of U or pi1 of V. So in particular, this is a word in the free products. It might be reduced, it might be unreduced. Okay. And moreover, F is homotopic to the concatenation product of all of these, right? So by that, I will call a factorization of F, right? So in the first statement, we showed that any F has a factorization. That was the surjectivity of capital phi, right? Any F has a factorization. So some comments: a factorization of F is a possibly unreduced word in the free product, right? Which maps to F by phi. That's what it means for it to be homotopic to the product of each loop in X, right? So again, we proved that every F has a factorization in the first statement. Two factorizations of F will be called to be equivalent if they are related by a sequence of the following moves. Okay, so first we can reduce in the free product. Let's recall what that means. That means combining successive loops, bracket Fi and bracket Fi plus 1, into a single loop, Fi times, or Fi concatenated or multiplied with Fi plus 1. If both of these are in the same group, pi1 of U or pi1 of V, right? If they're in the same group, I can multiply them in that group. That's a reduction as we discussed before, right? In the free group. Or this is a new kind of relation. We can regard Fi, suppose Fi lies in U, and then we can regard it as also lying in pi1 of V if Fi is a loop in the intersection, or vice versa. That if I have a if Fi is a homotopy class in V, which happens to live in the intersection, I can regard it as an element of the other group, pi1 of U. This will produce different elements in the free product, right? Now I have like, I'm changing, I have a sequence of words. Sorry, I have a word like Fi, F1, F2, I don't know, F3, something like that. And let's say this lives in pi1 of U, this lives in pi1 of V, I don't know, and this lives in pi1 of U. Then I'm saying that I'm calling two factorizations equivalent if, for example, if this F2 happens to lie in the intersection, I can consider it as an element of pi1 of U. But that will be a different element in the free product, right? However, so doing the first move does not change the element in the free product because that's just reducing. However, doing this second move of regarding something in the other group, if it happens to lie in the intersection, does not change the element in this quotient. So let me explain that. So why is that? Note that any product or any element in the free product induces an element in the quotient, right? By taking its associated class in this quotient. And now I claim that this move 2 does not change the element in this quotient. So what does that mean? So for example, suppose I start with so suppose I start with something that looks like that, a product that looks like this, where Fi happens to be a loop in the intersection, right?
Sorry, are these different I's now?
Different I's from where?
IU.
IU is different from I. Yeah.
Yeah, okay.
Yeah.
Of course, one's like a map.
A map. The other one's an index.
Yeah, I know, but I guess I was just confused by the notation. So
one, I mean, like technically it should be like iota, right? Or
yeah.
something.
Let's say these are iotas. Let's yeah. Anyway, yeah. If it has a U, it's a different symbol, so it's fine, right? So
yeah, I just wanted to check.
Yeah. So we want to prove that if we have a loop, a sequence of loops like that, and Fi happens to be a loop in U intersection B, then recall that iota U is the map from the intersection into U, and similarly iota V, right? So I claim that I have an equality like that, considering this as an element of U, or considering this as an element, considering this as an element of pi1 of U, or considering it as an element of pi1 of B in the quotient. Once I pass to the quotient. Why is that? I have to check that. So what do I have to check in order for this to be an equality in the quotient? Well, I have to check that if I multiply this times the inverse of that, I get something in N. Right? It's the identity in the quotient once I kill N. Right? So that's what I'm going to argue, right? If you look at this string times the inverse of that, that's the inverse. When I take the inverse I switch the order, right? And I take the inverses at each term. But now these start canceling, right? Fk cancels with Fk minus 1. Fk minus 1 cancels with the inverse of Fk minus 1 and so on. And I get to a sequence of symbol that looks like this, right? All the intermediates between IU of Fi and IV of Fi inverse cancel, right? And then I get a bunch of terms here, which are exactly the inverses of the terms here. In other words, I can write this as G IUFI times IVFI inverse times G inverse, where G is this sequence, this first sequence of elements in the free group, right? And this, by definition, is an element in N, in the normal subgroup, right? So that means that once I pass to the quotient, this is the identity, right? So in the quotient, that times that is the identity, which means that that equals the inverse of that.
Is that supposed to be F1 inverse at the end of that string? So we have F1 up to IU, Fi.
Yeah.
Okay.
Thank you. F1 inverse here. Good catch. Does that make sense? That if I have a loop that lies in the intersection, and I consider it either in U by applying this map IU, or either in V by applying the map IV, I get equal elements in the quotient. Okay, so let's go back. So now again, two factorizations of F are equivalent if they're related by reducing a word in the free product. That does not change the element in the free product because we can always reduce, right? Or regarding some Fi as lying in the other subgroup, the other group, sorry, if it happens to lie in the intersection. So 2 does not change the element in the quotient. Of course, 1 does not change the element in the quotient either, because it does not change before taking the quotient. Okay? So what do we want to prove now? We want to prove that given any F, any loop, any homotopy class of loop in the fundamental group of X, any two factorizations of F are equivalent. That would mean that this map induced in the quotient, sorry, this map induced by phi from the quotient to pi1 of X is an isomorphism, right? We already showed it's surjective, the map before taking the quotient, right? It's surjective. So now I'm saying, oh, if I take any two pre-images, they will be equivalent. Any two factorizations, they will be equivalent. Maybe let's use a different symbol for equivalent. If I take any two factorizations of F, let's say these dots are factorizations of F, mapping to F by phi, I claim they are equivalent.
You're kind
that
of
means they define the same element in the quotient.
This isn't a check for injective though, right? This is like you're checking that it's well defined now that we're quotienting.
I'm checking that it's injective on this quotient. Yeah. Does that make sense or not? Let me go again.
No, I mean, I guess the way I normally do injective is I assume that the two outputs are the same and then prove that the two inputs are the same. And
yeah, so let me formulate it in that way. So suppose we have this, yeah, let me erase the squiggle. Suppose we have phi, you have two factorizations. and suppose they are the same, right?
You want tilde though, right?
Yeah, I'll say it in this way. Well, it's the same. You'll see. Oops. Maybe this is a different thing. Suppose these are the same. First of all, what does that mean? That they are homotopic, right? They map to the same, let's say, the same F. Suppose they're the same. Now, injectivity for phi would mean proving that these two things inside are the same as well in the domain of phi. But I'm not proving that. What I'm saying is that they are equivalent in the quotient. So they are the same in this quotient. So now I can say it by placing the tildes and saying, oh, suppose these are equal. So I'm going to show that these two are equal in the quotient. Which are, assuming these are representatives of elements in the quotient, I'll show that they're equivalent in the sense I just introduced before. Does that make sense that this is injectivity now? So let me write it here more clearly. So assume we're going to show this, assume we have that, then these are the same in the quotient. More precisely, I'm going to show that then this is equivalent. They're related by a sequence of the moves 1 or 2 above, right? Okay, that's what I'm going to show. And that will show that this map is an isomorphism, or equivalently that N is the kernel of phi.
Just to make sure I understand, you're not assuming that, like, you're using FK and I think F, is that L, or are you saying?
Yeah,
FK
FK and FL. I mean, these are two factorizations. Factorizations are words of any length, right?
Yeah, I'm just saying we're not assuming that they're not the same length or anything.
No, not at all. Yeah. Any two sequence of loops, either in U or V, which are homotopic to F. That's what I have. Then I want to show that they're equivalent. In other words, they define the same element in the quotient, right? Okay, so let's do that. So bear with me now. It's a cute argument. So suppose we have, again, two factorizations, f1 up to fk and f1 prime up to fl prime. These are two factorizations of the same element f. So in particular, they're homotopic in X, right? Via some homotopy from the square into X, right? So these are two loops in X, right? Because each term is a loop based at x0, right? Like each fi and each fi prime or each fj prime is a loop based at x0, right? Some of them are inside U, some of them are inside V. So the composition of all those, or sorry, I should use the word, the multiplication of all those are is a loop, are two loops based at x0. And they're homotopic, right? Because these are two factorizations of F. So let capital F be a homotopy between these two factorizations, which happens to be loops. Now we do the usual trick, right? Or the usual argument. By the Lebesgue number lemma, we can find partitions of the interval S0, S1 up to Sm and T0, T1 up to Tn, such that each rectangle of the square are ij. So two partitions of the interval give you a partition of the square into rectangles, right? So consider each of these rectangles Rj is mapped into U or into V by F. This is always possible by the Lebesgue number lemma, using compactness of the square and using the covering U V of X, right? So this is always possible. We've seen arguments using this this Lebesgue number lemma in the same way. So suppose we have that partition. Moreover, I'm going to assume that the subdivisions are fine enough in the following sense. I'm going to assume that we have taken common subdivisions with those giving the products F1 times F2 all the way to Fk, and the corresponding product with the F primes. What does this mean? Each of these products give you a partition of the interval, right? Remember how I defined the product? Like this should have, technically, it should have like parentheses like that all the way, right? I do, in the first half, I do F1, and in the second half, I do the rest, right? And then in the next fourth, I do F2, and in the next fourth, I do the rest, and so on. So that induces a partition, right, of the interval. And I'm taking the common subdivision with the ones given up here. So pictorially, what does that mean? So here, the black segments denote the partitions of the product. For example, in this first half, I do F1. In this next fourth, I do F2. In this next eighth, I do F3. And the rest, I do F4, right? That's how I define a product, right? So we also have another partition given by the above, S1, S2, the blue segments that can be anywhere. I'm just saying we take the common partition. We take all of these segments. Is that okay? And that's your new partition. So I will assume we have done this already. Okay. Okay, good. So as I said, any partition, any two partitions of the, given two partitions of the interval, you obtain a partition of the square into rectangles, which I'm going to label in this way. 1, 2, 3, 4, then I move up 5, 6, all the way. I'm going to label my rectangles in this way. Okay? Remember, what's the property of this partition? That each rectangle gets mapped by F into U or into V. Right? So now, so let's see. So first of all, this is, so you have F here, right? This was the homotopy between those two factorizations, right? So that means that, let me maybe use blue here or red. This bottom edge gets mapped to what? By F. This gets mapped to, maybe I'll do it like that, F1, F2, the first factorization, right? Okay, and this top edge gets mapped by F to F prime 1 all the way up to FL prime, right? Because this F was chosen to be a homotopy between these two paths. And these, maybe let me use green, maybe. These two segments get mapped to X0, the base point, right? Because this is a homotopy in pi 1 of X. It's a homotopy of, path homotopy of loops, right? So all this gets mapped to X0, all this gets mapped to X0. X0 is a point, is the base point here, right? Okay, so now I'm going to consider the path, which I'm going to call gamma r in the square, separating the first r rectangles as follows. So for example, gamma 2 separates the first 2 rectangles from the rest in this way. That's gamma 2, okay? Formed by the straight line segments. Gamma 3 would be obtained from gamma 2 by pushing this into this square, and gamma 3 would look like that, right? Gamma 4 looks like that, right? Gamma 5 looks like that. It separates the first R rectangles with straight line segments going along these lines in your partition, right? Gamma 0 would just be that. It separates 0 rectangles from the rest. And the last gamma may be gamma mn. Gamma mn would just be that, the top edge.
Do the gammas all start and end at the bottom left and right corners, or do they start along the side of different places?
No, they start along different places.
Okay. So
this is this is gamma
so like
5.
Yeah, okay. So it doesn't go down from there, I guess, because that's how you do it for a couple of them. But
it has to separate the first 5 rectangles from the rest. Okay. Gamma 5.
So gamma 4 is just the straight line between the 2 rows, not down to the corner.
I don't think it matters.
I guess they're homotopic, but
I mean, all of these are homotopic, but what I'm saying, it doesn't matter. It's because you can take it to be like that. Yeah. It doesn't matter because all this segment, remember, all of this gets mapped to x0.
Oh, yeah. Got it. That was, I think, what I was...
That gets collapsed to the same point. So,
okay, yeah, that
but
makes
for
sense.
consistency, yeah, let's say they end like that, you know, like they don't have to go down. Yeah. It's the shortest path that separates the first R rectangles from the rest. How about that? Shortest path. Yeah. So for example, gamma 5 would be something like that. Yeah, that's better. Shortest path separating the first R rectangles from the rest. Okay, so gamma 0 is that bottom edge. Gamma, the last gamma, which is m times n, is that top edge. So I have all of these paths. And then I can restrict f, right? F is a map from the square to x. I can restrict f to each of these paths. And that will give me a loop in x0, right? Because these edges all get mapped to x0. So for example, gamma 2 in this picture gets mapped by f to a loop as x0, right? So all of these are loops in X. The map that I obtained by restricting F to those segments, right? Okay, and now I'm going to do one more thing, and then I'm going to tell you how this will be used to show what we want. Remember, we wanted to prove that these two paths are equivalent in this sense that I described before. Okay, so bear with me. So now let me call the corners, all of these corners, vertices of the subdivision, okay? These are the vertices, all the corners of the rectangles. So for each vertex V in the subdivision of the square, such that V gets mapped by F to a different point than x0, I'm going to choose a path GV from the corresponding point in X to the base point. Okay? If V happens to lie in U, I'm going to choose that path to lie in U. I can do it because by assumption, U is path connected. If V happens to lie in capital V, I will take that path to lie in capital V. And if V happens to lie in the intersection, I will take that path to lie in the intersection of U and V, which I can do because I'm assuming the intersection is path connected. So all these vertices here get mapped to points in X. Some might be X0, okay? For those, I will not do anything. For the ones which are not X0, I'm going to choose a path to X0, okay? Which lies in the corresponding subset, U, V, or the intersection of U and V. Okay, so what am I going to do with this? I'm going to construct a factorization of each of these loops in X. Remember, by restricting F to each gamma R, I obtain a loop in X. And how do I construct that factorization? I'm going to give a picture soon. So I'm going to insert the inverse of G followed by G, or let me say the inverse of GV followed by GV into this path at the successive vertices that I see on the path gamma R. This factorization will depend on certain choices, but all will lead to equivalent factorizations. So let me explain this in terms of a picture. So I look at gamma 2, right? Remember, for each vertex, I have chosen a path into X0 from the corresponding vertex into X0, okay? So I look at gamma 2. That gives me, gamma 2 gives me a loop in X0, right? Now, I have chosen these G's like that. Right? That's how I chose G's. And they lie either in U or V or the intersection of U and V. Right? All of these red paths. And then I'm constructing a new factorization of this path, right? Which is given by what? It's a sequence of loops now. It's first this loop, right? That's the first loop in the factorization. Then the second loop goes in the opposite direction here, then goes here, then goes here. That's the second loop. And the third loop does something like that, right? And the fourth loop does something like that. And the last loop in this picture does something like that. Okay? So given these red paths, which I'm calling G, GV, right? I get a factorization of this loop. What's a factorization again? It's a sequence of loops, each lying inside U or V, that is homotopic to this loop. That's a factorization of this loop, right? And I've just described one. So what's the point now? The point is that the factorizations of these factorizations that I have described by choosing these paths of F at gamma R and the next F at gamma R plus 1 are equivalent. Why is that? Because how do I pass from, let's look at the blue path here. How do I pass to the next one? I pass to the next one through a homotopy in R3 in this picture. But R3 by assumption lies inside some U or some V. Lies inside U or inside V, sorry. So this homotopy can be taken in U or V, right? So that means that like this, the parts in the factorization corresponding to these segments, for example, can be replaced inside the same U or inside the same V by another homotopy class, which will be that. Right? Together with the maps G, with the maps G at the vertices, of course, because I want them to be loops at every loops in U or loops in V, right? Okay, so passing from f at gamma r to f at gamma r plus 1 yields one of these moves, right? I'm just replacing, it yields equivalent factorizations. Because it changes the path f of gamma r to f of gamma r plus 1 by a homotopy within U or V, right? So now I put all of these together and note that the factorization of the bottom edge, f restricted to the bottom edge, is equivalent to the first thing I started with. The factorization of the top thing, of the top edge, top horizontal edge, is equivalent to the second factorization I had. And I described the sequence of equivalences between a factorization corresponding to this one and a factorization corresponding to that one. And that yields that these two are equivalent in that sense. So I know this is a lot to digest. If you got lost, you can go back to, I'll send you these notes and I'll upload this video. Are there any questions about the argument? There's something I went a little bit fast, and it was this point. Let me take 3 minutes. So I described this factorization of each f restricted to gamma r, right? I look at gamma r, as in the picture below, this blue path here. F restricted to it gives me a loop. And I construct a factorization by choosing paths, right? A factorization is a sequence of loops, each either on U or on V. There's a choice here to make, right? Because what if like, what if this point here, for example, gets sent to the intersection of U and V? I'm considering the factorization as a sequence of loops, each either in U or either in V, right? So for example, if this point, if this vertex here goes to the intersection of U and V, the GV I'm taking lies in the intersection of U and V by the choice I've made, right? So I have to make a choice here. Either I will consider it as in U or as in V, but they are equivalent. Any two choices, right? Because this actually lives in the intersection, right? So remember this move number 2. If something lives in the intersection, I can choose it to live in either of the groups, and I will obtain equivalent things by definition of equivalence, right? So that choice is irrelevant up to this notion of equivalence. So any choice will lead to equivalent factorizations. And that's all I want. I want a sequence of equivalent factorizations like that. Oops, like that. A sequence of equivalent factorizations connecting the bottom one to the top one.